I obviously forgot. So now this is what we are dealing with. This is what the structural mechanics team will be doing now. Uh, this is a model version, and we need the structural mechanics team to give us this modeled version. Everything like this was made with a piece of paper. You understand? These fins were cut with papers. This body shape itself was molded with paper to say wrap and tape a tube of paper around the film canister. You understand? So this everything here was molded with paper. So this will give us an idea of what to expect if we eventually get PVC pipes. So for this design, they call this I think the design phases. How many of us remember that? The initial design. Oh God, yeah, I'm going to school. I've forgotten design phases. So conceptual design, no preliminary design. I think it's conceptual, preliminary, then detailed. Blah, blah. So this might be our conceptual design now. Just us using, sorry, just us using papers to actually get around what we need to do precisely. So that's what this is all about. So I will show you another video now. So basically, structural team, what will be expected from you from as a follow-up from today's meeting is we expect you to give us a drawing, a sketch of what the rocket will look like. Please, structural team, take notes. And for you to be able to do that, you need to research on YouTube, watch videos, watch. It's these things are very simple. Just watch videos, see how they build these things, and give us your own personal sketch. Like I said, you don't have team lead now. It all depends on how whoever does the best job. That's it. So the sketch will be given to the aerodynamics team to model something like that. So the sketch you all agree on, because the sketch will be sent to the group, the different sketch you guys make, the different designs. And you should know it's pretty simple to sketch things like this. You just make it 2D. I mean, you would draw it like this, just shapes like this, something like this, something like this, something like so this might be your sketch. This is very very disorganized. This is not even worthy to be called a sketch. But this might be what you are looking at tentatively. You understand? But of course, there will be a mid section here. You understand? I'll show you some things that will be inside this place because the question a lot of you will be asking now is what will be inside this place, Gogon? It can't be empty. So this is where our parachute will be. The rocket motor will extend here like this. So I'll show you another this thing now. So this design will be given to the aerodynamics team to work with it. So they will simulate it or check out existing simulations online. You can use AutoCAD if you are good with AutoCAD. You understand? You can use Ant Sketch if you are good with Ant Sketch. It would be nice. It would be really nice if you guys can unmute your mic so that you'll be able to talk. Because now I have to constantly check the chat screen to see what you guys are saying. So if you know your background is mute, please just your background is okay. Just unmute your mic so we can talk and interact. It's a team section. All right. So you basically you can use AutoCAD. You can use any simulation. If you make it 3D for us, it will be more awesome. You understand? At least, but for the conceptual design, you understand? Just give us a 2D at the very least. You understand? So maybe a preliminary design, you can now give us something more detailed from your side. Here you get. So that might be it anyway. So afterwards, when we are done with this, do we all understand the concept of everything here? Or are there any questions on all this? Do you understand the whole thing? Everything? All right then. So moving on, I will proceed to share another image now to show you what will be inside. So this is another type of rocket. You can see this. This is the same thing as that one basically. It's only that this one is the 2D version. You can see this one is 2D. This one is not symmetrical. It does not have a plan. It does not have a symmetric view. Yeah. So this is 2D. So sorry. So this is you can see this is the nose cone. This is the payload section. If there's anything I want to put there, this is the body tube. We don't need this payload section. So this place will just be straight for us. We don't need to put all this demarcation. If you want to do a two-stage rocket, the second stage will be around here. Let me use my pen. The second stage will be here. The first stage will be from, this will be the first stage. This is a rocket motor if you don't know. So this will be the first stage from this point to this point. From this point to this point. So from this point to this point will be the second stage. You understand that? So from this point to this point will be where our parachute and everything will be. But we are building a one stage rocket. So we will have our this recovery system. You can see is attached to something here. This is just a parachute. And we are going to build that ourselves too. But for the very first launch, we won't use a parachute. We just want to see if we can really get something high up there. You understand? And that's exactly why we are going to be building from something very cheap, very, very cheap. And we are not going to be attaching any serious mechanism on it. And we are going to use a sort of proportion that won't get it to a very high feet, just 1000. Then lastly, as a precaution, we are going to be launching on an open field. So it can be um that that indoor sport area. There are a lot of open fields there, and we can use this thing too. We can use engineering side too. We just need to use a place whereby it will be free of distractions. You understand? A place whereby you can safely launch and regain our chute. So I sincerely hope that you are jotting some things down. Anyway, this thing is being recorded. So we already talked about this is the parachute system. We craft it for our second launch and we put it inside this payload section. I'm trying to admit new people there. So now these are the fins, like you see. These are the fins. I'm sure you can see that. These are the fins. That one. So depending on the nature of what we are building, we are going to be using four fins. You understand? But it all boils down to the aerodynamics team, and these things are important. The aerodynamics team should be able to simulate for two fins, for three fins, for four fins. Which one gives the best aerodynamic stability? You understand? And how do you measure aerodynamic stability? Aerodynamic stability is a measure of pressure acting on equal parts. You understand now? So if you're using one fin, the pressure acting on the side of the rocket will be more than the other side. So in other words, it can tilt over. If you're using two fins, depending on the distribution, since depending on the this thing, if you're using two fins, the aerodynamics will be different. The pressure acting on one side, we are building a 3D rocket. It's not 2D. It's not like we are crafting a paper in XY plane. Do you understand? Let me use my pen to explain what I'm saying. This is XY plane now. So if you wanted, we can just do something like this. This is not what we're trying to build. We're trying to build something in XYZ plane. You understand? So we are looking at something three-dimensional. So that means forces will be acting on the three planes, on the X plane, on the Y plane, and on the Z plane now. I'm trying to give me a sec, please. Okay. So for example, this is what we are looking at now. You understand? So our rocket will be something like this. So forces will be acting here, forces will be acting here, forces will be acting here. You understand? So if you use two fins, the pressure acting on the rocket at the z-axis will be different. If you use three, it will be different. If you use four, it will be different. If you use five, it will be different. If you use so many fins, it will be too aerodynamically stable and it creates drag. Because I know most of you must be asking that, okay, why can't we just use 10 fins to be okay, to be on the safe side? If you use too many fins, it will create drag. They call it induced drag. Aha. So, and matter of fact, if you watch rocket launch videos, you will discover that most times, For the first stage booster, it usually has more fins than the second stage booster. How many of you noticed that? Rocket launch videos, I mean, for NASA, for big corporations like that. The first stage booster usually has about four fins, then the second stage booster has like two. That's because when they want to eject the first stage, the first stage booster ejects just over the atmosphere, then second stage booster continues. When they want to eject the first stage booster, it is induced drag that causes the ejection, though there are other ejection mechanisms. But the drag from the four fins will be so much that once the first stage booster stops propelling the rocket, the fact that it's not generating any propulsion again, it will be forced to withdraw. Like the atmospheric drag will be so much that it will just push it down. You understand? So that's an ejection method. So that's why fins at the first stages are usually much more than the second stage. They can use about five or six fins at the first stage. Then you just see two at the second stage. That's usually how they do it. And there might not even be any fin at the second stage. They might be using attitude control flaps because rockets still uses flaps. This is what I mean by flaps. Some rockets has fins like this. Starship has it. If you have seen Starship has this. So at a particular point, this flap will just go up, this flap will just go up just to coordinate the orbit. So, but we are not doing any of this. This is basically what we are trying to build. This is a 2D version, but it will have four things like a suggestion, the aerodynamics team can determine on those. And the existing research, you don't need to be simulating everything. The existing research that determines the optimal number of fins that a rocket should have, a model rocket should have. Some will say six, they'll give their reason, some will say five. Just do your research. So I've told you what's expected from the structural mechanics team and the aerodynamics team now. Structural mechanics as a recap, please give us a sketch of what we are looking at launching. And the sketch should be drawn after you have done your research. Don't look at these pictures. Look at people that have actually launched model rockets online. Practically, look at it. Make reasonable deductions on what we can achieve. The height, the width, the diameter, the internal diameter. Give us all those things because we're engineers. Don't just give us a rough sketch and submit it. No. What should the internal diameter of the pipe be? The internal diameter of the payload section, this section, the internal diameter of this section will determine if you are buying a 5-inch PVC pipe, a 10-inch PVC pipe, or a 2-inch PVC pipe. You understand? Because I'm looking at getting all those materials this weekend. That's what we are really working towards. So that aside, the structural mechanics team will also determine, okay, how are we going to get the fins? Are we going to be using PVC materials for the fins? Are we going to be using cardboard for the fins? What sort of fins should we be looking at? What's the optimal one that we should be aiming for? I'm talking about the material now, not the aerodynamics. So once you do that, the nose cone section, so how do we get that? Are we using a cup for that? Are we using this? Are we using that? So that will all be part of your sketch. So I expect to see things like this. Let me give you a draft. I expect to see things like this. I expect to see something like diameter 15. You understand? Diameter 15, material PVC. I'm sure we can all see that. Diameter 15, material PVC. Then what else? I also expect to see things like this. Please, are you all listening to me? Can you all hear me, please? Okay. So I expect to see things like this too. The length from the nose section to the section just above the fin, the height. You cannot give me height of something like 10 meters or anything. You understand? So you look at the nose cone too. So for the nose cone, you can tell me the material will be PVC. For this now, we have covered the height, the diameter, and the material of the payload section. You understand? Now we are talking about the nose cone. So you can tell me the material for the nose cone is PVC. I'm trying to clean for the payload, so I'll be able to write. So the material for the payload is PVC. You can tell me the diameter Because the diameter is not regular, you can just tell me the base diameter. The base diameter is 2 inches. You can tell me that the height is 2 meters. So this is what we just expect. So you now come here to for the fins. You now tell me the fin. The material is PVC. We are not, of course, not PVC, but just as an example, you can now tell me the length. Now, you should know that the fins actually looks like a wing. You understand? So for starters, because we are just starting out this thing, I would allow you to use things like length. But for second launches and third launches, we start using things like aspect ratio. We start using things like, yeah, so we just get there. But now you can just tell me that the length from year to year of the fin, sorry. You are talking about one fin, no? So you can just tell me the length from year to year is 2 meters. You understand? And you can tell me the height of the fin, the base height. That is the height connecting to the rocket itself. I'm talking about this height. So you can just tell me the height is 1 meter, something like that. So this is what I expect to see from the structural mechanics team. So give us the sample while sending your sketch. So it will enable us to work towards that. Any question from the structural mechanics team? All right. So moving on, the aerodynamics team will now come up and um with their own analysis of our rocket. So they will tell us that um our rocket should be, if our rocket is traveling at Mach 0.7 and we are using PVC, and our fin, and we are using PVC, we should be expecting that it should be able to get to an altitude. You now give us a, this is your analysis. This is called preliminary analysis. So you have done the examining of everything. So you now tell us you should be expecting an altitude of between 500 feet. Aerodynamics team, listen to me. Oh. You tell me we should be expecting an altitude of between 500 feet to 1,000 feet based on your research online, because you've seen rockets of this particular height built like this and everything, and this is the altitude it got to. So you now tell us that you think from your recommendation that number of fins, the first thing was altitude, number of fins, equals to 2. You understand now? Is an example. Of course, you're not using 2, but number of fins equals to 2. Then you now tell me that nose cone section, nose cone should be blunt. You understand? So you tell me the nose cone should be blunt. So these are analysis. You just look at the material, everything we are using from A to Z, and you tell us what we are going to be needing for it. You understand? The nose cone section, because you are dealing with aerodynamics. So every part of the body, you understand? You look at it. What if this thing is flowing through air? For starters, these things I said, they are just the important things, so you can just work on that. But at later levels, we'll be needing to do something more advanced. For example, you need to actually simulate this. For starters, I can allow you not to simulate it. You understand? You can just do your research online. But after the first launch, the data we gather will allow us to better iterate through these designs and simulate better ones. So now we have this, and I think aerodynamics is well taken care of. Um, Now moving on to the proportions team. If you can look at this part, you will see something attached. That's the rocket motor. I will send a video to the group, and Samuel will update you on the materials needed for the proportions later. But then you should research personally too, please. So what I'm expecting from the research team is propellant. Proportions team, listen to me. What you now do is you will tell me that you have a sheet of paper now, or a Word document. You will tell me proportion analysis, proportion analysis for, what should we name our rocket? I haven't thought about that. But proportion analysis for A. If A is the name of our rocket, proportion analysis for A. So you underline it, you underline that. Afterwards, you now tell me that uh propellant, you put a bullet point like this, propellant, we are using uh ammonium something something plus sugar. You understand? So on the second line, you now tell me weight of materials, like weight of propellant. So you tell me we need 20 grams of ammonium nitrate. You understand? 20 grams of sugar, something like that. Now, the funny thing is, all these are actually available online. If you watch one YouTube tutorial, you get everything. But I need everything in writing. I need to do your analysis. So you will tell me the weight of sugar we're expecting, the weight of ammonium, blah, 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 we're expecting. Next, you will tell me, based on things you have seen and the analysis you have done, this specific, because you have written the material, the propellant, and the grams of each. So you now tell me expected altitude equals, aerodynamics team gave us an altitude. So it will now give us your expected altitude based on your propellant. So you tell me 300 feet to 1000 feet. You understand? So you can see it's very simple for everyone. So that's just what we are doing basically. I want us to learn from scratch. You understand? So once we do this, the subsequent rockets we are launching, it will give us better ideas on what we did wrong the first time, where to get it right now. So I've covered the three things. Do we have any question before we end the meeting? I told you our meetings will be very short. No long talks, no long conversations. Do we have any questions at all? Oh, 5 minutes, 5 people remaining. Any questions at all? I'll send the video of the meeting to you so you'll be able to do justice to it. How are you going to cross the two altitude? What two altitude? You can unmute your mic and talk. I don't understand what you're asking. Which two altitude? I remember that aerodynamics team will be giving us an altitude, expected altitude, and propellant team will be giving us an altitude too. So say something, please. Yes. See, what we are doing is both of them will give us expected altitude. You understand? So we are going to build the rocket and we are going to launch it. You understand? Eventually, we will compare the range of altitude of these two teams. Èyí tó bá wà more accurate. You understand? We'll just look at it. Okay, the propulsion team, they said this should get us to a height of 300 feet. We'll get to us 300 feet. We go to 200 feet. What went wrong? What were the calculations? How many grams of this one did you mix with this one to get us to this feet? You understand? I mean, if all the materials we used, maybe you used 20 grams of ammonium something, then 50 grams of sugar, that's 80 grams, then maybe 20 grams of water, that's 100 grams, and that got us to 900 feet. Does that mean if we multiply it, or if we double it, if we turn it to 200, will that get us to a higher altitude? Does that mean it will get us to altitudes of, I mean, the first one got us to 1000 feet. So if we double it, will it get us to 2000 feet? If we triple it to make it 300 grams, will it get us to 3000 feet? That's what I mean by iteration. You understand? We did optimization. So that's the process of optimizing. You understand? We've done our conceptual design, preliminary, we've tested it. So we've now gotten data as feedback. We now want to re-optimize and go back to preliminary design again. You understand? So that's what we are doing on that. So it's not like the two of them will just give us altitude based on this material. This is the altitude we are using. And structural mechanics team too, please try to get the weight of the materials you'll be using, the weight of the nose cone, the weight of the payload section, just the weight of those different sections. If you can't, it's still fine. But if you can, try to get us there. So any other questions from anyone? Waiting. Please unmute your mic and talk. We are chatting. Just let's interact. Another question. So the deadline, I told you I'll give you a deadline. The deadline for this is today is Wednesday. So please by Thursday evening, that's tomorrow evening. These things are very simple, like I said. So by Thursday evening, please all of you submit your reports so that this weekend we are going to work towards getting those things. And we'll have another meeting on Friday. So if you're able to submit your report on Thursday, we are going to work on it. You understand? We are going to set feedback to each team. Then we are going to arrive at the final design for our rocket. So by Friday, whenever we have a meeting, we'll be here to discuss. Here's what we are concluding on. This is the picture of the rocket we are building. This is the picture of the propellant. This is the cost of everything. Cost of PVC, cost of this, cost of this. You understand? So that will be able to meet up with the time frame. So that's the idea. All right. So are we all satisfied with that? Thursday evening, everyone will meet up. Are we all satisfied? In fact, this thing will take less than 10 minutes. Less than, if you devote your time to do the research, less than 10. Okay, maybe the research will take you 30 minutes. But you writing and jotting is just 10 minutes. That makes it 40 minutes. And I'm giving you guys way more than 24 hours. You are not working as a team now. Just submit your own. You know the team you belong to. You know that you picked structural mechanics team. So, and I've outlined what structural mechanics team is supposed to be doing. So just do your own thing and submit. You understand? Submit to me or send it to the group. You understand? I would know if you did your own research or you just copied from another teammate. I will definitely know. So you can use Word document or you can just write it on a sheet of paper, snap it and send it. Anyhow, I'm trying to let us work very fast. You understand? So please, that would also be okay. So you don't need to know your teammates, talk with your teammate. No, you understand? You can ask questions on the group, you get, but not like we don't need that yet. You get. I'm trying to hasten us up so that when we resume, we know that first week of resumption like this, bam, anybody that is around. In fact, the only reason why we might not launch is because some people are not around. I want to wait for them. We don't want to be showing them video. That might be the only reason why we might not launch. But it won't be because there is no material or we don't have the money to do it. No, 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 no. That might be the only reason because we want everybody to experience at least the very first one. You understand? So that's it. Do we have any other questions, please? All right, in the absence of none, I want to appreciate you all for attending the meeting. I do not take this for granted. It took sacrifice, and I'm really, really grateful. Thank you all. And this is truly adventurous. And the truth is, when people start out doing something, they don't know how it will end. They don't even know if it will be worth it, let me use that word, or not. They don't even know if eventually it will be something. But I want to tell you, this will be worth your while. You understand? This will be really, really worth your while. It will be something you look back 2 years to come and you'll be really glad you did this. If you understand. So on that note, I want to say thank you all for attending the meeting tonight. If you have any other questions, you can send it to the group. Have a very good night. I'll be expecting submissions from every single person interested in this tomorrow evening. Thank you all. Have a very good night. Thursday, 6 p.m. is the deadline. Thank you.